Welcome to Grab and Go Info. Hypothesis testing has become an indispensable tool for businesses seeking to optimize their user experience. Whether you're an aspiring analyst preparing for your next interview or a seasoned professional looking to brush up on your knowledge, this comprehensive guide on hypothesis test interview questions and answers is for you. You'll be well equipped to demonstrate your expertise. So, let's dive in and unlock the secrets to acing your next hypothesis testing interview. Let's get started. Question 1. What are the key components of an hypothesis test? 1. Control group and treatment group. The control group is exposed to the current version of the product, feature, or design, while the treatment group experiences the modified version. The goal is to compare the performance of these two groups to identify which variant is more effective. 2. Hypotheses. Hypothesis testing involves formulating hypotheses about the expected outcomes. The null hypothesis typically states that there is no difference between the two variants, while the alternative hypothesis asserts that there is a difference. 3. Key performance indicators or metrics to measure success. KPIs are quantifiable measures used to evaluate the effectiveness of the tested variants. Examples include conversion rates, click-through rates, bounce rates. The chosen metrics should align with the objectives of the hypothesis test and accurately reflect user behavior and preferences. They should also be easy to measure, has low fluctuation, and the impact happens in a short time period. 4. Sample size and duration of the test. The sample size is the number of participants in each group needed to achieve a statistically significant result. The duration of the test depends on the desired sample size and the time required to obtain statistically significant results. It's important to run the test for an adequate duration to avoid biased conclusions. 5. Statistical tests to determine significance. Statistical tests like t-tests or z-tests are used to analyze the results and determine if the observed difference between the two variants is statistically significant, that is, not likely due to chance. This helps in making data-driven decisions about which variant is more effective. Question 2. How do you determine the sample size needed for an hypothesis test? The sample size can be calculated using the formula below, where z1 minus alpha divided by 2 is the z-critical value for the two-sample test at the significant level of alpha. z1 minus beta is the z-critical value for the statistical power of beta. Sigma square is the variance, and delta is the absolute difference between test and control. N is the minimum sample size needed for one group. For a two-sample test with significance level of 5% and power of 80%, the formula approximate to n equals 16 times sigma square divided by delta square. Question 3. How do you choose the appropriate metrics to measure the success of an hypothesis test? 1. Align with test objectives. Choose metrics that directly relate to the specific goals or hypotheses you are testing. For example, if the test aims to improve user engagement, a suitable metric might be time spent on the site or pages viewed per session. 2. Focus on actionable metrics. Select metrics that, if improved, would have a direct impact on your business objectives. Actionable metrics can help guide decision-making and facilitate data-driven improvements. 3. Consider primary and guardrail metrics. Identify primary metrics that align with the main objective of the test, and guardrail metrics that help assess any unintended consequences or side effects of the changes. For instance, while the primary metric might be conversion rate, guardrail metrics could include average order value, bounce rate, or customer satisfaction. 4. Ensure measurability and reliability. Choose metrics that can be accurately measured and collected using available tools and data sources. Additionally, ensure that the metrics are reliable and not subject to significant random fluctuations or external factors. 5. Opt for a mix of quantitative and qualitative metrics. While quantitative metrics like click-through rates, conversion rates, or revenue per user are essential, we should consider including qualitative metrics such as user feedback, surveys, or usability scores to provide a more comprehensive view of the test's impact on user experience. 6. Segment metrics when appropriate. Depending on the test's goals, it may be necessary to segment metrics by specific user groups, traffic sources, devices, or other relevant factors. Segmentation can help identify variations in the test's impact on different segments, enabling more tailored decision-making. 7. Keep it simple and focused. While it's essential to cover all relevant aspects, avoid choosing too many metrics, as it may dilute the focus and make it difficult to draw clear conclusions. Limit the number of metrics to those most relevant to the test's objectives and those that can be clearly interpreted and communicated. Question 4. What makes a good metric for hypothesis test? A good metric for an hypothesis test is one that 1. Directly relates to the test's objective, ensuring that the metric is relevant and meaningful for the specific context and goals of the test. 2. Is actionable and easy to measure, enabling data-driven decision-making and facilitating the implementation of improvements based on the test results. 3. Accurately reflects the impact of the treatment, providing a clear and reliable measure of the changes being tested. 4. Exhibits low fluctuation or noise, minimizing the risk of drawing false conclusions due to random variations or external factors. 5. Shows impact within a relatively short time period, allowing for timely analysis and decision-making without excessively prolonging the test duration. Question 5. What are some commonly used metrics for hypothesis test? 1. Conversion rate, the percentage of users who complete a desired action, such as making a purchase, signing up for a newsletter, or filling out a form. Conversion rate is a commonly used metric in hypothesis testing focused on optimizing user flows, landing pages, or calls to action. 2. Click-through rate, the ratio of users who click on a specific element to the number of total users who view the element. CTR is useful for evaluating the effectiveness of ad creatives, calls to action, or navigation elements. 3. Average order value, the average amount spent by customers per transaction. AOV can be a valuable metric in hypothesis testing aimed at optimizing pricing strategies, upselling or cross-selling techniques, or product bundling. 4. Bounce rate, the percentage of users who leave a website after viewing only one page. Bounce rate can be useful for assessing the effectiveness of landing pages, website design, or content quality in engaging users and encouraging them to explore further. 5. Time on site or session duration, the average amount of time users spend on a website during a single visit. This metric can be helpful in evaluating the impact of changes to content, site structure, or design on user engagement. Question 6. Can you explain the concepts of statistical significance, confidence level, and power in the context of hypothesis testing? Statistical significance measures the likelihood that the observed difference between A and B is not due to chance. Confidence level represents the probability that the true population parameter falls within a confidence interval. Power is the probability of correctly rejecting the null hypothesis when it is false. Question 7. What is the difference between a one-tailed and a two-tailed hypothesis test? When would you use each? A one-tailed hypothesis test checks for an effect in one direction. For example, test is better than control. A two-tailed test checks for an effect in either direction. For example, test is different from control. Use a one-tailed test when you have a specific directional hypothesis, and a two-tailed test when you are interested in any difference between the two groups. Question 8. What is multiple testing problem in hypothesis testing? The multiple testing problem arises when you perform several hypothesis tests simultaneously, which increases the likelihood of encountering false positives. Let's illustrate this using an experiment where you test 20 different hypotheses. Suppose you are running an online store and want to evaluate the impact of 20 different design changes on the conversion rate. For each design change, you perform a test and calculate a p-value to determine if the change has a significant effect. You use a significance level of 0.05, meaning that you are willing to accept a 5% chance of making a type I error for each individual test. Now, when you perform 20 independent tests, the probability of making at least one type 1 error increases. To illustrate this, consider the probability of not making a type 1 error in each test, which is 1 minus alpha equals 0.95. The probability of not making any type 1 errors across all 20 tests is 0.95 to the power of 20 equals 0.358. Consequently, the probability of making at least one type 1 error across the 20 tests is 1 minus 0.358 equals 0.642 or 64.2%. As you can see, the likelihood of encountering false positives has increased substantially due to multiple testing. This is the multiple testing problem. Question 9. How do you handle multiple testing issues or the problem of false discovery rate in hypothesis testing? Method 1. Bonferroni correction. This method adjusts the significance level by dividing it by the number of tests being performed. The adjusted significance level is then used to evaluate each individual test. Although simple, the Bonferroni correction can be overly conservative, increasing the likelihood of type 2 errors. Method 2. Home Bonferroni method. The Home Bonferroni method is a stepwise modification of the Bonferroni correction that maintains better statistical power. For this method, the p-values from multiple tests are sorted in ascending order. Each p-value is then compared with the adjusted significance level, where rank is the position of the p-value in the sorted list. The first p-value that is greater than the adjusted significance level and all subsequent p-values are considered non-significant. Method 3. False discovery rate control. FDR-based methods control the proportion of false positives among the rejected null hypotheses, rather than controlling the family-wise error rate. This approach is less conservative and has higher statistical power. Method 4. Benjamini-Hochberg procedure. The Benjamini-Hochberg procedure is a widely used FDR controlling method. Like the Home Bonferroni method, p-values are sorted in ascending order. Starting from the largest p-value, it is compared with the adjusted significance level, where rank is the position of the p-value in the sorted list. The first p-value that is less than the adjusted significance level, and all smaller p-values are considered significant. Question 10. What are some common pitfalls or mistakes to avoid when conducting randomized controlled study? 1. Insufficient sample size. Running an hypothesis test without enough participants can lead to inconclusive results and a higher risk of type 1 and type 2 errors. It's essential to calculate the required sample size based on your desired statistical power, significance level, and minimum detectable effect. 2. Short test durations. Ending a test too soon may not capture the full range of user behavior or account for factors like seasonality or day of the week. Determine the appropriate test duration based on the required sample size and ensure that you run the test for the full period. 3. Peeking at results. Checking results before the test is complete and stopping tests prematurely can invalidate your findings due to an increased chance of type 1 errors. Stick to the predetermined test duration and avoid making decisions based on partial data. 4. Not accounting for novelty or learning effects. Users may initially react positively to a new feature due to its novelty, or take time to adapt to the change. Run the test long enough to account for these effects and ensure the observed differences are not temporary. 5. Multiple testing issues. Performing many tests simultaneously increases the likelihood of false positives. Use techniques like the Bonferroni correction, home Bonferroni method, or false discovery rate control methods to address multiple testing problems. 6. Inadequate randomization. Failing to properly randomize users into control and treatment groups can introduce selection bias and affect the validity of your results. Ensure that users are randomly assigned to groups to minimize bias. 7. Overemphasis on statistical significance. While statistical significance is crucial, it's also essential to consider the practical significance and effect size. A statistically significant result may not always have a meaningful impact on business metrics or objectives. Question 11. Can you explain the impact of peaking on the test results? 1. Increased type 1 errors. Peaking and stopping the test prematurely based on observed significance increases the probability of making a type 1 error. This means that you might conclude that there's a significant difference between the groups when, in reality, there isn't one. 2. Insufficient data. Stopping a test early due to peaking may result in an insufficient sample size, which can affect the test's statistical power and increase the risk of type 2 errors. This means you might fail to detect a true difference between the groups when one actually exists. 3. Biased results. Peaking and making decisions based on partial data can introduce biases into the test results. The observed significance might be due to random fluctuations in the data or external factors, leading to inaccurate conclusions. 4. Incomplete representation. Stopping a test prematurely may not capture the full range of user behavior or account for factors like seasonality, day of the week, or learning effects. This can result in a skewed representation of the population, affecting the generalizability of the test results. Question 12. What is p-hacking? P-hacking, also known as data dredging or data fishing, is the practice of manipulating data analysis or selectively reporting results to find statistically significant findings when they may not genuinely exist. It's a form of research misconduct that can lead to false discoveries and misleading conclusions. P-hacking can occur through various practices, such as 1. Multiple testing. Conducting a large number of tests on the same dataset increases the likelihood of finding at least one significant result by chance alone. 2. Selective reporting. Only reporting the results that are statistically significant, while ignoring or suppressing those that are not. 3. Data peaking. Continuously checking the data during an experiment or study and stopping when a significant result is found, which can inflate the rate of false positives. 4. Cherry picking. Selecting specific data points, variables, or subgroups that produce significant results while ignoring others that do not. 5. Post hoc hypothesizing. Formulating a hypothesis after observing the data, rather than before, and then presenting it as a pre-specified hypothesis. Question 13. What do you do to ensure valid hypothesis testing? 1. Predetermine sample size. Before starting the test, calculate the required sample size based on the desired statistical power, significance level, and minimum detectable effect. This helps to minimize the risks of type 1 and type 2 errors and ensures that the test has enough data for reliable conclusions. 2. Establish test duration. Set an appropriate test duration based on the required sample size, expected traffic or user engagement, and any potential external factors such as seasonality or day-of-week effects. Running the test for a sufficient duration helps capture a representative range of user behaviors and experiences. 3. Randomization and consistency. Ensure that users are properly randomized into control and treatment groups, and that the test conditions remain consistent throughout the test duration. This minimizes the risk of biases affecting the results. 4. Monitor results for stability. Track the performance metrics of the test periodically to ensure that the results have stabilized and are not fluctuating due to novelty or learning effects. Ideally, the results should remain consistent and stable towards the end of the test period. 5. Resist peaking. Avoid checking the results before the test reaches its predetermined sample size or duration, as this can introduce biases and inflate the probability of type 1 errors. Stick to the planned duration and sample size even if the results seem significant early on. 6. Reach predetermined stopping criteria. Once the test has achieved the predetermined sample size, test duration, and stability of results, you can stop the test and analyze the outcomes. Question 14. What is sample ratio mismatch in hypothesis testing? Sample ratio mismatch occurs when the proportion of participants or traffic allocated to the control and treatment groups deviates significantly from the intended or planned allocation ratio. For example, if you plan to allocate 50% of the traffic to the control group and 50% to the treatment group, but due to an implementation error or other issues, the actual allocation ends up being 60% for control and 40% for treatment, then you have a sample ratio mismatch. Question 15. What is the impact of sample ratio mismatch in hypothesis testing? 1. Statistical power. A significant deviation from the intended allocation ratio can affect the test's statistical power, making it harder to detect true differences between the groups when they exist. This increases the risk of type 2 errors. 2. Test duration. When there is an imbalance in the allocation of participants or traffic between the groups, it may take longer to achieve the required sample size for each group, extending the test duration. 3. External validity. SRM can impact the external validity of the test results if the mismatch is caused by factors that systematically affect one group but not the other, introducing biases that limit the generalizability of the findings. Question 16. What's the statistical testing for sample ratio mismatch? The chi-square test is used to determine if there is a significant difference between the observed frequencies of events and the expected frequencies based on the intended allocation ratio. Here's a general outline of the steps to perform a chi-square test for SRM. 1. Determine the expected allocation ratio. For example, 50% for control and 50% for treatment. 2. Calculate the expected frequencies for each group based on the total sample size and the expected allocation ratio. 3. Record the observed frequencies for each group, that is, the actual number of participants or traffic allocated to each group. 4. Compute the chi-square statistic using this formula, where O represents the observed frequency, E represents the expected frequency, and sigma indicates the sum over all groups. 5. Determine the degrees of freedom for the test. In this case, degrees of freedom equals number of groups minus 1, that is, 2 minus 1, which equals 1. 6. Compare the calculated chi-square statistic with the critical chi-square value from the chi-square distribution table, using the appropriate degrees of freedom and significance level. 7. If the calculated chi-square statistic is greater than the critical chi-square value, the difference between the observed and expected allocation ratios is statistically significant, indicating a sample ratio mismatch. Question 17. How to address sample ratio mismatch in hypothesis testing. 1. Identify the cause, investigate the reason behind the SRM, such as implementation errors, technical problems, or issues with randomization. Understanding the root cause will help you address the problem effectively. 2. Rectify the issue. Once you've identified the cause, take corrective actions to rectify the problem. This might involve fixing bugs in the code, resolving technical issues, or ensuring proper randomization of users into control and treatment groups. 3. Monitor the allocation ratio. Keep a close eye on the allocation of participants or traffic between the groups throughout the test duration to ensure the intended ratio is maintained. Regular monitoring can help you spot and address any deviations promptly. 4. Adjust sample size calculations. If the SRM is significant, consider adjusting the sample size calculations to account for the imbalance. You may need to increase the sample size to maintain the desired statistical power and significance level. 5. Rerun the test. In some cases, it might be necessary to rerun the test after addressing the SRM issue. This ensures that the test results are based on a proper allocation ratio and minimizes the risk of biases affecting the outcomes. 6. Use statistical methods. Some statistical methods, like weighted analysis or resampling techniques, can help you account for SRM in the analysis phase. These methods can help you adjust the results to account for the imbalance between the groups. Question 18. What is an AA test? An AA test, also known as a null test or dummy test, splits your users or traffic into two identical control groups instead of a control and treatment group. Both groups receive the same experience, with no changes made to either one. The purpose of an AA test is to 1. Verify the accuracy of your testing tools and methodology. Running an AA test helps you ensure that your testing tools, randomization process, and data collection methods are working correctly, as there should be no statistically significant difference between the two identical groups. 2. Establish a baseline. An AA test provides a baseline for your test results, which helps you understand the natural variability in your metrics and set more realistic expectations for the randomized controlled tests. 3. Assess false positive rate. By comparing two identical groups, you can assess the rate of false positives in your testing process. If you observe a significant difference between the two groups in an AA test, it could indicate issues with your testing methodology, such as improper randomization or sampling biases. 4. Identify external factors. An AA test can help you identify external factors or events that may be affecting your metrics, such as seasonality, day-of-the-week effects, or other unforeseen variables. 5. When conducting an AA test, it is crucial to ensure proper randomization and data collection. If the results of the AA test show a statistically significant difference between the two groups, it's essential to investigate the cause and resolve any issues before proceeding with hypothesis tests. This will help ensure the validity and reliability of your testing process and results. Question 19. How do you decide whether to launch a product based on the results from a randomized controlled test? 1. Establish success criteria. Before running the hypothesis test, define clear success criteria, such as a statistically significant improvement in the key performance indicators relevant to the test, like conversion rate, click-through rate, or revenue per user. 2. Analyze the results. Once the test has been conducted, analyze the data and calculate the differences in performance between the control and treatment groups. Evaluate whether the results meet the predefined success criteria. 3. Check for statistical significance. Ensure that the observed differences between the control and treatment groups are statistically significant, meaning that the results are unlikely to have occurred by chance alone. Commonly used significance levels include 0.05 or 0.01, but the choice depends on the specific context and the potential consequences of type 1 errors. 4. Evaluate the practical significance. In addition to statistical significance, consider the practical significance or the real-world impact of the observed differences. Assess if the improvement in the KPIs is large enough to justify the cost and effort required to implement the changes. 5. Analyze secondary metrics. Look at the impact of the treatment on secondary metrics, which may not be the primary focus of the test but are still important to the overall user experience or business objectives. Ensure that the treatment does not negatively affect these secondary metrics. 6. Assess the generalizability. Consider whether the test results are likely to generalize to the broader user base or different segments of users. If the test was conducted on a specific segment, be cautious about extrapolating the results to other segments without further validation. 7. Perform a cost-benefit analysis. Weigh the potential benefits of launching the product, such as increased revenue or improved user experience, against the costs associated with implementing the changes, like development, maintenance, or potential risks. 8. Gather input from stakeholders. Collaborate with cross-functional teams, such as product managers, designers, and engineers, to gather their input and perspectives on the test results and the feasibility of implementing the changes. Question 20. What statistical test to use for an hypothesis test on click-through rate? The two-proportion z-test is appropriate for comparing proportions or rates between two independent groups, such as click-through rate. This test assumes that the data follows a binomial distribution, and that the sample sizes are large enough for the central limit theorem to apply, which allows us to use a normal distribution to approximate the binomial distribution. If you have made it this far, you probably find the information in this tutorial helpful. Please click the like button and subscribe to the channel to get notified when I publish new videos like this. To learn more about data science interviews, please click the YouTube playlist on the screen now. Thank you for watching and see you in the next video.